Good morning. So this is our 39th lecture, and in the previous lecture we have been discussing about the restriction based flow meters, and in particular the restrictions can be provided in multiple ways. So we discussed the three ways of providing restrictions. One was orifice plate, second was nozzle, and third was use of a Venturi meter. Okay, so the two has been discussed in the previous lecture. So now we will talk about Venturi meter. So as per the ASME standards, the dimensions of Venturi meter are given over here. So you can see it consists of three sections. So this is the first section. So here is a flange which will be connected to the pipeline, and then you have a converging section, and the angle of convergence is alpha 1, and alpha 1 varies from alpha 1 is generally kept as 21 plus minus 2 degrees. And then we have a constant section which is called as the throat, and you can see the two pressure tappings are used. One pressure tap is here having dimension delta, and this is the second pressure tap at the throat which is having dimension again delta. Okay, and then we have a diverging section, and in diverging section the angle is alpha 2, and the value of alpha 2 ranges from 5 degrees to 15 degrees. So the reason is, if we keep the low value of alpha, then this diverging section length will be very large in order to meet the pipe diameter. Okay, we cannot keep very high value of alpha, because if alpha is beyond a certain limit, say if this is my alpha, then I will be finding that in this particular zone, in actual scenario my velocity profile is like this. Okay, but if you see, this is a diverging section. So in the diverging section, what will be happening, the kinetic energy will be converted into the pressure head, and ultimately I will be finding increased pressure in the diverging section. Okay, so it means that as the flow is moving in the downstream direction in the diverging section, there what is happening, basically there the pressure is increasing. So I can say that flow is moving against the positive pressure gradient. Okay, so that is called as adverse pressure gradient, and if your value of alpha is greater than 15 degree, then because of the adverse pressure gradient you will be finding that there will be flow separation. The meaning of flow separation is, near the wall there will be negative velocity profile, and away from the wall there will be positive velocity profile. So it means that near the wall there will be certain amount of fluid which will start moving in the negative direction. That is called as flow separation. It mainly occurs because of the adverse pressure gradient. So if your flow is from left to right and the pressure keep on decreasing from as you move on right, that is called as favorable pressure gradient for the flow. But if your flow is from left to right and you experience that static pressure is actually increasing as you move downstream, in that case the pressure gradient is called as adverse pressure gradient. And if in any situation there is adverse pressure gradient, then there will be chances of flow separation. Okay, is this one clear? So uh, uh, in order to avoid the flow separation in the Venturi meter, its angle, particularly the diverging section angle, is limited to 15 degrees. Okay, one important point we would like to highlight, that why Venturi meters are having low head loss. The reason is, in case of nozzle and orifice, we were just providing this throat type restriction, and after that we were allowing the flow to expand by its own. But in this Venturi meter, we are providing a proper diverging section which will be guiding the flow streamlines in order to increase and reach to the pipe diameter. Okay, so this diverging section is something which is over here helping us in the significant amount of pressure recovery which was absent in the other two types of restrictions. Is this one clear? And typically if you talk about a Venturi meter, so the flow coefficient for Venturi meter varies from 0.98 to 0.995. So it means it's a very close value of the flow coefficient, because its structure and manufacturing is so precise that its flow coefficient is actually very narrow. Okay, and this is for Reynolds number greater than 2 into 10 to power 5. One important point, because of its complex structure and very smooth profile, this Venturi meter is having highest amount of cost. Okay, One another important point which I would like to highlight over here, whenever you put these type of restriction based meters in your flow networks, then in our flow network there can be pipe fittings present, there can be some elbows present. So if you have any pipe fitting or elbow present which is leading to the disturbance of the flow profile, then you have to provide at least 10D diameter for the smooth pipe section before putting a Venturi meter into the pipeline. And this value of smooth section, which should be provided after a pipe fitting or after a bend, may vary as large as 40D for the case of orifice plate and the flow nozzle. Okay, is this point clear? So this is very important point. You cannot consider that, say, flow has turned through a 90-degree bend and you immediately put a flow meter over there, because their streamlines will not be parallel to the smooth surface. So that's why your pressure measurements will be wrong. Moreover, the velocity profile will also not be fully developed, and then this assumptions of Bernoulli equation will also not be fully valid. So that's why what we need to do first, we need to straighten the flow, and to straighten the flow we need to provide the smooth section of the something about 10D diameter for Venturi meter and 40D diameter for the orifice or the flow nozzle. Is this one clear? Okay, so you can also see, as I told you that previously, that Venturi meters are having a lot of pressure recovery. So because of that, the permanent head loss in the Venturi meter will be very small. So that's why it's a low head loss device. So you can see the quantification for diameter ratio of throat to the pipe. You can see the permanent head loss. So for Venturi meter it is least less than 20, and for nozzle and sharp edged orifice it is the highest, and then it is for the nozzle. Okay, so it means that Venturi meters are having the least permanent head loss because of the presence of diverging section which is leading to the pressure recovery. So that's why Venturi meters will be consuming the less pumping power. It means these are having a less operational cost. Okay, but once again we have to also consider the lifetime into consideration before deciding a meter. Why? Because the Venturi meter is having the highest initial cost. So there should be optimization in between the operational cost and the initial cost based on the lifetime of the device. Okay. Okay, then another very new idea, though not new, it is not that much popularly being used, but still nowadays people have started using in various microfluidic devices, that is called as the laminar flow element. Okay, so the idea of laminar flow element is basically whatever the devices we have studied till now, Venturi meter, orifice meter, or the flow nozzle, in all these devices, because majority of the time our flow conditions are such that in practical scenarios that we are mainly operating in the turbulent regime. Okay, and the measurement of the velocity we are saying is directly proportional to the pressure head. Okay, so the idea is, in case of turbulent flow, pressure head is directly proportional to the square of flow rate. So it means that pressure drop and flow rate are not having linear relationship between them. Okay, so if pressure drop and flow rate are not having linear relationship, if you want to choose a discharge coefficient, a single unique discharge coefficient which you want to specify for your device, it is very difficult to select because linearity does not exist between the characteristics. So that's why these restriction based flow meters, particularly the Venturi orifice and flow nozzles, these are used for very narrow range of flow measurement. These cannot be used for the wide range of flow measurement. Okay. On contrary, we know that in case of laminar flow, pressure drop is directly proportional to the velocity or the flow rate. Okay. So if pressure drop is directly proportional to velocity, it means there will be always a linear relationship between the flow rate and the pressure drop if we are able to maintain the laminar flow conditions. Okay. So this type of principle can be used for measuring the flow rate for very wide range of flow rates. Okay, because in the entire range you will be having the smooth linear relationship between flow rate and the flow rate and the particularly pressure drop. Okay, so that is the reason we wanted to have the laminar flow while we are actually doing the measurement of the flow rate. So one idea is that we know that in case of laminar flow, pressure drop from laminar flow theory by using the parabolic velocity profile for a pipe, that flow rate inside the tube will be pi times diameter raised to power 4 divided by 128 mu L into delta P. So here you can see that flow rate is nothing but directly proportional to delta P. Okay. So what I can do, if I have a larger pipe section, in a larger pipe section I can fit a large number of smaller diameter tubes. Okay. So what will be happening, you know that if I use the Reynolds number formulation over here, so say if I use Reynolds number formulation at this section and say this section is having d diameter, okay, so what will be Reynolds number formulation in this section? Red will be equal to rho v d by mu. But if my whole cross section I have subdivided into larger number of small pipes, okay, so these are the large number of small pipes which I have fitted into my main pipe. Okay, so now the diameter of these individual pipes, so diameter of each pipe will be very small in comparison to total diameter of the pipe. Okay, so if this diameter is very small, in this way my Reynolds number of the pipe will be equal to, small pipe will be equal to rho v into dp by mu. Is this point clear? So my Reynolds number which is based on dp will be very small in comparison to Reynolds number based on diameter. Okay. So now if I select my dp in such a way so that corresponding to the maximum flow rate which is coming through this pipe, if my Reynolds number of dp is less than 2300, then I will be able to ensure that through these individual pipes I will be having nothing but the purely laminar flow. Is this point clear? I will be having nothing but pure laminar flow. Now what I can do, across this each smaller tube, I can simply measure the pressure drop, and that pressure drop will be directly related to the flow rate from the laminar theory. Okay. So this is the benefit in case of typically in case of the other restriction based flow meters such as Venturi or efficient flow nozzle, typically the range of flow measurement, like highest flow rate which we can measure divided by lowest flow rate which we can measure, that particular range is 4:1. But whenever you are using the laminar flow elements, then typically that range can be extended to 10:1. Okay, so it means we will be getting wider range when we are using the laminar flow elements. Is this point clear? Now next idea comes that earlier we were having the flow meters which were based on the restriction. Now there are certain flow meters which are called as linear flow meters. So we are having some flow element, and that flow element is having the linear motion, and depending upon its linear deflection we can say that what is the amount of flow rate. Okay, so I think all of you have seen the fluid mechanics lab over here. Have you seen? So in different devices you will be finding there is one glass tube, and inside that glass tube there is one ball, metallic ball or something hollow metallic ball, that is called as a float or a ball. Okay, and then if you see on that particular glass sheet there will be some scale also made. Okay, and in that scale either it is written LPH or LPM, so liters per minute or liters per hour, something like that. Okay, and then you can see that if you maintain the flow rate to some condition, that ball initially oscillates and finally it settles to some value, and then if we read corresponding to that we can know that how much is the flow rate. Okay, so that particular device is nothing but a linear flow meter, and it is called as a rotameter. So rotameter is very common device which is used for measurement of flow rate for both the liquids as well as the gases. Okay, so typically in a rotameter we have this type of, this shaded portion is nothing but shows a tapered glass tube. So what we have is a tapered glass tube, and this tapered glass tube is having capital D diameter at the bottom, and of course whenever this y, this is the y coordinate along the vertical direction, whenever the value of y is increasing, the diameter of this tube is actually increasing. Okay, so why this diameter is increasing, that we will see soon. Another important point is it is having some floating element which is either called as bob or it is also called as float, and this particular extended portion can be over here marked, can be scaled with this particular scale, and based on the scale we can see what is the value of flow rate. Okay, so what is the idea or how this particular device works? Okay, so if you typically see this particular float, what it is experiencing, it is applying certain amount of weight in the downward direction. Okay, so say if density of the float is density of this bob is rho b, its volume is vb into g. This will be the amount of weight which is acting in the downward direction. Okay, now it is present in a fluid medium, so of course it is displacing certain amount of fluid, so because of which there will be certain force, buoyancy force, which is acting in upward direction. So in upward direction I will be having minus rho f is density of fluid, and the volume of fluid is nothing but equal to vb only, that is the displaced volume, times g. Now I am referring to the situation when this float is in the equilibrium condition. So in equilibrium condition it will be stationary, so its weight, buoyancy, and there will be one more additional force. Though this float is at its stationary location, but fluid is continuously moving across it. Okay, so let me consider that the fluid which is moving across it, that is having average velocity um at any given flow rate. Okay, so um is the fluid velocity. So if um is the fluid velocity, this will experience certain amount of drag force because of the motion of the fluid in upward direction. Okay, so that particular drag force I can calculate as minus cd times, so what I am doing over here, all the forces which are in downward direction, that I have taken positive weight, and other, so I can take it downward as negative and others too as positive. Okay, so cd into half rho f, okay, into square. So cd is nothing but called as coefficient of drag into half rho f square. So that will be equivalent to the shear stress, and this when multiplied with the surface area of the this element, that will be giving me the total drag force. So these three forces for a given flow rate and at the steady condition must balance each other. So this will be equal to 0. So from here you can calculate the velocity will be equal to, what will be the value of from here? Will become equal to rho b minus rho f times vb into g multiplied by 2 and divided by cd into rho f into ab and square root of this. So this is how you can calculate the average velocity of the flow. Once you know the average velocity of the flow, your volumetric flow rate will be area times flow area. Now I have to write here flow area, AF times this average velocity of the flow. And how much will be flow area? So let me consider that this is the D as the diameter over here, and diameter of this particular tube at any other location is given by this linear function d plus ay, because tube is linearly tapered. Okay, so my flow area will be equal to pi by 4 d plus ay whole square minus small d is the restriction diameter. So flow is only happening through the gap in between this portion and the outer tube. Okay, so that's why minus d square. Is this point clear? So that will be my flow area. So this way I can actually calibrate this. Now the second question comes, why this particular float is, why this particular glass tube is actually tapered. Okay, so the reason is, say this balance of forces is happening corresponding to a Q amount of flow rate. Okay, now if you increase the flow rate to some another value Q dash which is greater than Q. So if you increase the flow rate to some other value Q dash, in that case what will be happening? Your value of UM will increase. If you have a straight tube, what will happen? If you have a straight tube, let's consider that you don't have tapered tube. Okay, so if you simply have straight tube, then corresponding to Q flow rate you have balanced when the velocity was UM. But if you have straight tube, then flow area will always remain the same. If flow area is always remaining the same, and if you increasing the flow rate, then your flow velocity UF dash will become greater than UM. Is this point clear? And if UF dash is becoming greater than UM is the velocity that is corresponding to the static balance of the float. If flow velocity is greater than UM, then this drag force will increase. The vertical force will increase and float will keep on rising to the top. That's why what we do, we provide this tapered portion. Because what will be happening, say if float was at this location 1, when I increase the flow rate, of course at this point it will experience velocity greater than UM. So this will start moving in upward direction. But whenever it is moving in upward direction, it is parallelly also experiencing the increase in area because of the tapered glass tube. When it is experiencing increase in area, that increase in flow area will decrease the flow velocity, and there will be a point when UF dash will reach equal to UM. And once this equilibrium is established, the float will stop. Say this is established at this point, so this will be now new flow rate corresponding to the new position of the float corresponding to the Q dash flow rate. So is this idea clear why there should be tapered glass tube? All are clear with this idea? Okay, so this is very fundamental flow meter. You all should know about this because you will be finding in almost every experiment of fluid mechanics we are having wherever there is the flow of the fluid, we are having this type of rotameter connected to different devices. Okay. And one more thing you have to see that because rotameter is here doing the balance of weight, buoyancy and the drag forces, so that's why it should always be oriented in the vertical direction. Okay, you cannot keep it in any other direction. Okay. Then other linear flow meter is a very simple one. So here you have a turbine. This is an impeller basically, and this impeller is acting like a turbine, and that's why we call this as turbine flow meter. So in this also what will be happening, your flow rate will be proportional to RPM of the impeller. So let me write RPM of impeller. So when you are increasing the flow rate, in the linear proportion your RPM will also increase. So this is a straightforward relation. You have linear relationship in between the flow rate and the RPM. So that is the reason we are calling this as linear flow meter. And one important point, you can see this is the first section. So in first section we have provided some channels, bifurcation. So these channels and bifurcations are provided in order to straighten the flow. Okay, so these are particularly provided to straighten the flow, and then after flow straightening it passes over the impeller, and impeller keeps on rotating. Then we have some magnetic pickup sensor over here. So this is used to rotate, used to note the RPM of the turbine flow meter, and depending upon the RPM we are having linear dependence with the flow rate. Okay, so this is a very simple device, which also you will be finding that rotameter is not having any digital signal which you can acquire during the transient operation. Okay, but as it is having some magnetic pickup sensor. So you can take the output of this magnetic pickup sensor as the continuous signal, and this can be recorded in the computer even during the transient operation, how flow rate is actually varying or fluctuating. Is this one clear? Okay, then we have traversing methods. So traversing methods, there are many advanced techniques also, such as laser, Doppler, anemometer, etc. But over here I will just give you idea about one very simple device which is called as Pitot tube, and how it is beneficial in traversing methods for measurement of the flow rate, that we will see. Okay. So we know that if we have to measure the pressure in any pipe, then what we do, we create some tap at the wall and we connect this tap either to a pressure gauge or to a manometer in order to measure the pressure. Okay. So typically we have seen that whenever we have to we have to create this wall tap, we have to consider the portion of the pipe where flow streamlines are perfectly straight. Because if flow streamlines are curved, then there will be variation at different sections in the pressure. So at every point pressure should be same, for that streamline should be straight. So at this point I can connect a gauge and I can measure the pressure. So the pressure which I will be getting from this point, that is called as static pressure. Okay, this will be nothing but my static pressure. So typically another arrangement which can be used for measurement of static pressure is, I can put this type of tube. So this type of tube I can insert inside my flow, and then this other end of the tube I can connect to a pressure gauge or a manometer, and in this tube I can have some small holes along its periphery, like these are the small holes which are along its periphery. So in this way also what will be happening, this small tube is actually having hole along the periphery, and over that streamlines are moving parallelly. Okay, so here also whatever the pressure I will be getting, that will be nothing but a static pressure. So that is all, that's why this tube is called as static pressure probe. Okay, now there is one more type of pressure which is called as stagnant pressure. So what is the meaning of stagnant pressure? Now if instead of this I put some tube over here, which is having some hole over here, so not at the periphery but exactly at the location which is facing the flow. Okay, so if I make a hole which is directly facing the flow and then I connect a pressure gauge, so here what will be happening, here you can see that at any point slightly upstream of the tube you will be having some pressure P. So that's why static head will be P by rho g, plus you will be having some flow velocity V, so some kinetic head V square by 2g, and whenever you reach this tube section, so immediately at the tube section what is happening, the flow is entering into the tube, and this tube is having some stagnant fluid which is connected to a pressure gauge. Okay, so say this tube is reading, this gauge is giving me the reading of some pressure P naught. So P naught by rho g, plus I also must consider some kinetic head. But will there be any velocity at this point? If you have any tube which contains stagnant fluid within it, and if this tube is facing the flow from the front, so what will be happening? Because this tube is already having some fluid filled inside it, so ultimately whenever the flow will enter into this tube, that flow will finally actually stop. So it means I will be having here zero velocity. So another kinetic head will be zero. Okay. So in this case, this tube is giving me some value of pressure which is P naught, and this value is nothing but the sum of static pressure head plus kinetic head. Okay, so this particular pressure P naught by rho g is something which is called as stagnation pressure head, and P naught is called as stagnation pressure. Is this one clear? All are clear with this idea? So basically what is the meaning of stagnation pressure is that if We are having the flow and we allow the flow to reach the rest condition in an isentropic manner. I will not go into that detail, but the fundamental idea is that if this type of tube arrangement I use, that I have a tube with a small hole which is directly facing the flow. Okay, so this small hole will lead to the complete stagnation of the fluid which is immediately ahead of this tube. Okay, so that's why whatever the pressure which we will be measuring from this tube, that will be nothing but my stagnation pressure. Is this one clear? So the pressure which I will be getting from this tube, that will be nothing but my stagnation pressure. All are clear with this idea? Now the benefit is, if I know the stagnation pressure at any location and the static pressure at that location, then what I can calculate? I can calculate the value of velocity. What will be velocity from here? So if you use a device which can measure both stagnation pressure as well as the static pressure, okay, so then no, we want to measure the stagnant pressure. That's why we have used this type of device which is actually making the flow stagnant. Okay, so our idea is to measure the stagnant pressure. That's why this device is facilitating the flow to become complete, to reach at complete rest and give us the value of stagnation pressure. Because if the flow is not coming to complete rest, then we will not be able to measure the stagnant pressure. Okay, why we are doing this, you will be understanding in the next slide, because this gives us the value of local velocity. Okay, so from this equation I can tell that if I know the stagnation pressure and if I know the static pressure, then my velocity will be nothing but square root of 2 times P naught minus P. Is this point clear? All are clear with this idea? So from this equation, I will be getting velocity is equal to square root of 2 times P naught minus P. So it means that if you have a device which can give you the stagnation pressure and the static pressure, with that you can calculate the V value of velocity. Okay. So here now you can see the arrangement. So if you use this type of tube, so this type of tube will give you total pressure drop, and this type of wall mount will give you the static pressure. So this type of arrangement is called as total head tube. On contrary, this both things can be done by using a single tube. You can have one single tube. So this is the central tube which is directly facing the flow. So the central tube will give me nothing but P naught pressure, stagnation pressure. And I can have outer annular tube, and this annular tube can have small holes along its periphery which are parallel to the flow. This is not directly facing the flow, but this is parallel to the streamline. So the smaller holes which are parallel to the streamline, these will be giving me nothing but my static pressure. Okay. So once I know the stagnation pressure and the static pressure, then I can simply calculate that my velocity at this particular location of the flow is nothing but equal to square root of 2 times P naught minus P. Okay. So it means that Pitot tube is a device which is giving you the local velocity of the flow. Please remember this point very carefully. So restriction based devices, Venturi meter, orifice meter and the flow nozzle, these were giving you the average velocity of the flow. What was the average velocity at any cross section? Because while we studied their formulation, we worked based on the average flow condition. On contrary, here what we are doing is, here we are actually trying to measure the stagnation pressure and the static pressure at a given location in the flow. So that's why this will be giving us the local velocity of the flow. Okay. Now, one confusion can come to your mind that I am measuring the stagnation pressure at point B and I am measuring the static pressure at point C, which is slightly downstream of this particular pipe. So yes, this is correct. this differences between points B and C will be introducing some error. Okay, but we have to keep these holes slightly below the main leading edge, so that whatever the disturbance in the flow has come because of the presence of this tube, that settles down, and my streamline should become perfectly aligned at the point where I am measuring the static pressure. Is this point clear? Because if you keep this hole at very close to point B, then there may be curved streamlines which will be giving you the wrong value of the static pressure. Okay, so that is the reason. And if you want to utilize the Pitot tube, so the benefit of Pitot tube is that if you have, say, a pipe, at a pipe you can vary the location of Pitot tube to multiple points. You can traverse Pitot tube at different locations within the pipe. And if you are able to traverse this Pitot tube within the various locations, then you can obtain the values of velocity at different points, and you can construct your complete velocity profile. So that is the benefit of this. Okay. So Pitot tube is very, very fundamental arrangement which is used for measurement of the local velocity. You will be finding we have one setup in our lab also, where we are having the measurement of velocity using the Pitot tube. Okay, so whenever you will be doing your lab course on thermofluids lab, there you will be finding this. But particularly one thing I would like to highlight, that this is not the only arrangement in traversing methods which can be used. There are more advanced techniques such as thermal anemometers, laser Doppler anemometers, etc. Particularly for traversing methods, and in the linear methods there are electromagnetic flow meters, ultrasonic flow meters, magnetic flow meters, etc., which are used nowadays for measurement of the flow rate with better accuracy and for different types of scenarios. For example, we will not be always be having the pure flow of the fluids, like pure water or pure gases are present. We may have some systems where within the fluid some suspended particles are present. There can be hydraulic slurries. So depending upon the applications and the amount of accuracy needed, we can use the different types of flow measurement devices. Okay, but these are beyond the scope of this course. Okay, now we will start our next topic. So next topic is flow past immersed bodies. So say till now what we were studying is we were having a pipe, and inside the pipe boundary layer was growing from different portions of the pipe wall, and ultimately the maximum growth of the boundary layer was limited till the center line of the pipe. It cannot grow beyond that, because after that you will be having the presence of the two boundary layers will meet each other, and once the two boundary layers met each other, after that you will be having the whole regime which is dominated by viscosity. Okay, but in case of external flows like flow over aeroplane, flow over cylindrical pipes, flow over spheres, etc., we are not having any restriction for the growth of the boundary layer. It means boundary layer can grow up to any extent. Okay, and moreover, say if you talk about flow of aeroplane, so below the aeroplane you can consider huge distance is there. So even if you consider that, say, boundary layer of the aeroplane is say 1 meter thick, though it will not always be, because aeroplane moves at very high velocity. So when velocity is high, then thickness of boundary layer is small. That we will see subsequently, but just I am giving you one crude example, that even if you think that your boundary layer over the aeroplane is of 1 meter thickness at any point, still your aeroplane is having significant amount or infinite amount of fluid available above and below the boundary layer present. So it means that in case of external flows, whenever we will be studying the effect of boundary layer, it will not be, the flow will not be purely viscous dominant. Okay, outside the boundary layer there will be always some inviscid region present. So whenever we are having the combined presence of the viscous and the inviscid region, then what we have to do during this combined presence of viscous and inviscid flow, because the viscous flow analysis will be extremely challenging within the boundary layer. So we have to take some help of inviscid portion. We have to derive certain parameters from inviscid portion which will be acting as input to the viscous portion, and by doing the patching in between the viscous and the inviscid portion, we can obtain some theoretical solutions of or approximate solutions of our flow profile within the boundary layer. Okay, so let's see one by one the different cases. So first case I have considered over here is flow past a sharp flat plate. So you can consider this is a sharp edged flat plate, and length of the plate is L, and the distance along the length of plate is X, and let me consider that my flow velocity is very small. So flow Reynolds number, which is calculated based on the length of the plate as length scale, so rho v L by mu, it is only equal to 10. Okay, so in this type of scenario you will be finding that whatever the boundary layer is present about this, that is actually very very thick. So you have a thick boundary layer present. It means that delta is of the order of L. Is this one clear? So delta and L are comparable to each other. So here you will be having a thick viscous region, and then outside you will be having some inviscid region. Okay, and within the viscous region you can see that your velocity will be less than the free stream velocity. This u over here is called as the free stream velocity, and outside the boundary layer we will be having velocity value will be reaching to free stream velocity, and typically we define this dashed line as the boundary layer. So this boundary layer is considered at the point where velocity is almost 0.99 times of the free stream velocity. Okay, so all the gradients of the velocity will be existing only within the viscous region, and in outside inviscid region we will not be having any gradients of velocity present. Is this point clear? Now I can have another situation where I have the same plate but my Reynolds number is very high. So flow Reynolds number is close to 10 to power 7. Okay. So in this scenario, what you will be finding that whatever the viscous region or boundary layer region we are getting, that is actually very very small and confined to very small thickness near that. So here my delta is very very small in comparison to L. So it may be 2 or 3 orders smaller than the length of the plate. Okay. So in this case you can see that the gradients are in very narrow region, and then outside I have nothing but the free stream velocity. Okay. So now what are the implications of these two conditions? If you see one very very interesting point, if you see this blue colored line, so in case of thick boundary layer, this blue colored line is the streamline which is coming out from the free stream that has to deflect through a larger displacement. Is this point clear? So this line over here is actually displacing through a larger displacement. So flow over the boundary layer has to go through a larger displacement because of the presence of thick boundary layer region. On contrary, when your Reynolds number is large, then your boundary layer thickness is so small that streamline which is going outside can move in a straight manner. Okay. So what is the benefit of this? The benefit of this is whenever further we will be deriving the theoretical understanding of boundary layer theory, we have to know pressure gradient within the boundary layer. Okay. So what we typically do, we consider that whatever the gradient of pressure is there in the inviscid region, that we simply substitute into the boundary layer region also as a driving potential, and based on that we solve our boundary layer flow. Okay, so that in subsequent discussion I will explain it to you. But the idea is, because here flow streamlines are almost straight, so because of the straight nature of the flow streamlines, I will be finding that pressure at every point will be same at any x. So that's why this assumption of calculating pressure drop in outside inviscid region and then substituting it back into the viscous region to calculate flow parameters within the boundary layer is correct. But if you have larger deflection of the flow, then of course at every cross section your flow, your pressure will not be same at every point in the vertical direction. So because of this, I cannot correctly make the approximation of calculation of pressure outside boundary layer and then its substitution within the boundary. So that's why whatever the boundary layer theory we will be studying in the subsequent discussion, that will be applicable only for Reynolds number greater than 1000. Is this point clear? So for Reynolds number ranging from 1 to 1000, there is the applicability of boundary layer theory is not there. Okay, so in subsequent lectures I will be defining boundary layer theory, and boundary layer theory is mainly governed by patching of pressure from the inviscid region into the viscous region. So this type of patching will not be possible with good accuracy for the thick boundary layer regime, and typically the thick boundary layer regimes are obtained in case of Reynolds number range of 1 to 1000. So 1 to 1000 Reynolds number range, the boundary layer theory does not work, it works greater than 1000 only. Okay, and typically, so this is the relation of delta by x. It means that any arbitrary value of x, if you have to calculate the boundary layer thickness, then for laminar flow conditions it varies 5 by Reynolds number x power 1 by 2, and for turbulent flow it varies as 0.16 by Reynolds number power 1 by 7. Okay, so both these relations in the subsequent lectures we will be deriving from the boundary layer analysis, from the boundary layer theory. Okay, so you can see for different values of Reynolds number, these are the corresponding thickness values, and somewhere close to 3 into 10 to power 6 Reynolds number. This is the critical limit of Reynolds number for a flat plate flow. Up to this limit my flow will be laminar, so that's why you can see up to this I am writing the laminar flow theory thickness, and above this my flow will be turbulent, so that's why I am using the turbulent relation in this table. Okay, and typically you can see the thickness of the boundary layer in turbulent regime is more smaller in comparison to the thickness of boundary layer in the laminar regime. So that's why boundary layer theory is applicable for almost the entire turbulent regime, but one limit is there. Till now we have studied Reynolds number up to the range of 5 into 10 to power 9 for the flat plate flows. Beyond this, till now Reynolds number studies are not done. Okay, so I will stop and then we will have subsequent discussion in the next lecture.